for our next problem, we'll be working problem 5 in chapter 3. This problem states that we'll be calculating the effective pH on delta G naught ATP hydrolysis at pH 7, and this is accompanied by a release of hydrogen ion into the medium. The reaction is given by ATP plus water yields ADP plus hydrogen phosphate plus H plus. Okay, so if the delta G naught prime for this reaction is negative 30.5 kilojoules per mole, what is delta G naught? That is the free energy change for the same reaction with all components including H plus at a standard state of 1 molar. So we'll get back to that in just a minute. Alright, so let's look at these equations that were given. We can relate delta G to delta G naught by this equation, delta G equals delta G naught plus RT ln of products over reactants. So if we consider that if we are at standard state, we can say the KEQ is given by reactants, products over reactants. Okay, and so for delta G naught prime, we can say that our KEQ prime is given by KEQ times the hydrogen ion concentration. Why is this? Because remember, delta G naught prime are standard conditions where everything is at 1 molar except our H plus concentration, and for our H plus concentration, that's going to be 1 times 10 to the minus 7. So we can say if B minus and A are at 1 molar, then they're going to cancel out, obviously, because it's just 1, and so we'll be left with the H plus concentration. Okay, and so delta G naught prime is given by, then, delta G naught prime. If those are our new conditions, we can plug delta G naught prime in here, which is given by delta G naught prime is equal to delta G naught plus RT ln of the H plus concentration, because delta G naught prime is where everything is at 1 molar concentrations, except because of biological conditions, we have our H plus 1 times 10 to the minus 7. Okay, so we can say delta G naught prime is equal to delta G naught plus RT ln of H plus, because everything else is going to cancel out under those conditions. Okay, so this is for where hydrogen ion is produced in that reaction. Okay, so if it's consumed, then we can relate KEQ to KEQ prime up here. We can say KEQ is equal to KEQ prime times hydrogen. So we can solve for KEQ prime and get KEQ is divided by H plus is equal to KEQ prime. And we can plug that in for our KEQ. Okay, and so by rearranging, we're going to get then that delta G naught prime is equal to delta G minus RT ln of H plus if H plus is consumed in the reaction. So basically, if H plus is released, we're going to get this equation, delta G naught prime is given by delta G naught plus RT ln of H plus. Okay, if we have H plus consumed, then delta G naught prime is equal to delta G naught minus RT ln of H plus. Okay, so one of them gives us a plus sign if it's produced, if hydrogen ions are produced, and if they're consumed, we get a minus sign. So that's the takeaway from this. So in this case, we actually are producing hydrogen ion. Okay, and so we have the equation. We're going to be using this equation. Delta G naught prime is equal to delta G naught, okay, plus RT ln of H plus. But because we are actually given delta G naught prime, we're going to solve for delta G naught. Okay, and so we have to rearrange the equation. So let's do that. Let's look at it and rearrange it. Sorry, that's from the last one. Let's go down a little bit. Okay, so let's go ahead and write everything down before we get started. So we were told that our pH is equal to 7. And that means our hydrogen ion concentration is equal to 1 times 10 to the minus 7. Okay, the confusing thing about that is that, let's look at this problem again. It says that our pH is equal to 7, and it's accompanied by a release of hydrogen ion into the medium. But then it says down here, all components including H plus are at a standard state of 1 molar. So this problem is not stated correctly. What they mean is that all components are at the delta G naught prime standard state, okay, and everything except H plus is 1 molar, because it says it's at pH 7, and the study guide works this with a hydrogen ion concentration of 1 times 10 to the minus 7. So this problem is incorrectly stated, and we're going to work it as though it says just pH 7 here, okay, and everything else is 1 molar. Alright, so let's go ahead. So let's go ahead and write delta G naught prime, is equal to delta G naught, okay, plus RT ln of H plus, okay. And we were given a delta G naught prime equal to negative 30.5 kilojoules per mole. Okay, we're told pH is equal to 7, which means our H plus, I already wrote that down, is equal to 1 times 10 to the minus 7. And we were told T is equal to 298 Kelvin. Okay, and we know R. Alright, so we're going to be using this equation, but we were given delta G naught prime, and we were looking for delta G naught. Okay, so if we want delta G naught, then delta G naught is going to be equal to delta G naught prime minus, because we're going to move this RT ln of H plus to the other side, minus RT ln of H plus. Okay, and so delta G naught is equal to negative 30.5 times 10 to the third joules per mole Kelvin, so we can keep our units straight. I'm sorry, joules per mole. Okay, minus 8.314 joules per mole Kelvin times 298 Kelvin. Okay, I should move everything over, times the ln of 1 times 10 to the minus 7. Okay, hopefully we can see that. Alright, so that's going to be equal to 30.5 times 10 to the third plus, I got 39934.2, okay, which is equal to negative 9434.2 joules per mole. Is that right? Yeah. And that's going to be equal to 9.4, let's erase that, 9.434 kilojoules per mole. Okay, so I think the most confusing thing about this problem, okay, is that you have to figure out which equation to use and why you're using it. So you have to rearrange this equation. Okay, and the next thing is the problem was not stated correctly, so that you actually cannot use the H plus concentration as 1 molar. You have to plug in the pH 7 concentration, which is 1 times 10 to the minus 7 molar for our hydrogen ion concentration. All right, that was problem 5.